Hello there, and welcome to another problem session. So today we have a problem which is a little bit ill-posed, and this comes to us from IIT Joint Entrance Exam Advanced Physics. Okay, and this is 2021 exam, I believe. Okay, so this is actually a superconductor. This ring is superconductor, has no resistance, and expels all magnetic field. So magnetic flux through this, if you have this magnetic moment, then say you have magnetic. I'm going to draw closer so it's easier to see. I'm going to draw this bigger. So this is magnetic moment, and it's going to have its magnetic field lines like that. So this is going to make, and some of the magnetic field lines will go through this area, and there will be some magnetic field lines go like that, which doesn't go into that area. So it's kind of tiny magnet. You can think of this as a tiny magnet, and that's what's going on. But if it just sits there, no magnetic flux is changing, right? So imagine this thing was over here, and you're just moving to there. So this is some velocity v, and so only a few of these fields will make it when it's far away. And the way I've drawn is, let me draw this. When it's nearby, there are more field lines that go through it. More field lines go through it. So because magnetic flux is changing, you might say, one way to think about it is in the ring, so phi b through ring will change, and you say d phi dt will not be zero. That just, this will be equal to EMF induced, and this will be some resistance of the loop times the current in loop. So you would say, if resistance is zero, then there will be no current in the loop, right? So you can think of this way, but it says something different. So this route is not going to tell you what the current will be in the loop. It says this material is such, this material is such that is the current that it gets induced, it's got its own magnetic field. So let's see its magnetic field. Let's draw it with using some other ring, like this. So its magnetic field will just be opposite. That means the current induced will be this way, and magnetic field of these guys will have the same flux as the magnetic field. So phi b through the ring, so if you look at phi b through ring, is phi b of this yellow type and phi b of the orange type. So phi b from this dipole moment, which is m, I should use this color m. So, and then plus, this is self, phi b from I induced from m. So and it says this stuff, if you read it here, it says that stuff is actually the current gives rise to magnetic momentum ripples. Okay, but a closed loop wire does not allow any change in the flux through it. So this total is 0. It says this total is 0. So whatever that is, it remains, and then so change in this. So this equal to, we'll just say equal to 0. Equal to 0. So that's the condition it says, and so this will be like a B from M at the center of the B from M vector field times the area. So if the n hat is like, let's see, n hat is pointed this way, so this is going to be positive for this M, and times the area of the loop plus B from I induced, and this is going to be exactly opposite. This is going to be opposite direction. Dot n hat area loop equal to 0. So we can just ignore the area loop, and so this will say B magnitude wise, B from M at center of loop equals to B from I at center of loop. We'll just assume it's from the way it describes is, you assume that whatever the value as the center is a value across. You're just supposed to assume that. So this might give us the current, okay? So because this will depend on the current induced, and this will not depend on the current induced. And formulas for these are already given here. So this particular, so I'm not really going through it, just trying to understand what these things are here, and then we'll try to answer the question. So one of the question is, as it's moving, when M is at distance R, what's the current? So this equation should help me solve this problem. And this one is saying, well, keeping the loop at one place, and you're gonna bring this bring this dipole from infinity, from way out here to here. How much work will be done? Right? It says bring in dipole from infinite distance r. So how we can do is, like, if this is the force, so to answer this question, we just integrate the force on M by this current loop, which you can assume as a little dipole. So this from here, we just assume that you have M here, and this ring, we can replace that ring by a little dipole. So this is dipole this direction, and this dipole that direction, because magnetic field is in the opposite direction. So this is like M from the current, and this is M, physical M. So the force between these two guys, if the distance is r, is given by this formula. So all I have to do is I have to integrate this from infinity to r. So if I do this, I should have solved that. So that's my strategy. So this direction doesn't go anywhere. If you Faraday law and try to do that, it will not go anywhere. But these might go. Okay, let me try to erase and see if I can implement this and get a formula for current and formula for this. And we don't need to know the full formula, but we can just derive the whole formula. All right. Okay, so to answer question 1, so to implement this guy, how can we do it? To implement this guy, all right, so we need a B from M, so B from this at the center of that. So B from M is a formula is given here. It's going to be like that. Mu naught O over 2 pi M over R cube. And on the right side, we want, you have a current going this way, and I want to know magnetic field at the center. That distance is A, and so we're going to use, we will use Biot-Savart law, which is mu naught I over 4 pi, integrate over this loop, and dl, which is like a small element dl, but that's crossed into this r hat vector, and then that's the displacement vector magnitude. This is just equal to a, little a, so this is just equal to little a, and this r hat is unit vector, and right hand rule will give you. So if you work this out, it's going to be mu naught over 4 pi I, and this whole thing will be just 2 pi a, that's the whole length of the wire, and divided by a square. I think this is correct. So from this you get a 2 here, and this 2 cancels out, and this a cancels this 2, so this just remains a. This mu naught go away, so I equals to a over pi m over r cube. So that means I goes as m over r cube. And so when you look at over here, we see this is the answer, right? This is the answer, A. So A is the answer. Okay, let's try to do number 2 problem. Okay, to answer number 2, we're given the force between, if I have m1 here and m2 here and a distance r, then we've given the force. But we have this and m, and that distance is r. So we'll convert this into that. So this will be m1 will be I times pi a square. So we have m1, so now m1 and m2 is just going to be m. And since I is related like that, so this will be a over pi m over r cube pi a square. So it's kind of like that. So pi goes away. So this is m time a cube over r cube. So that's the m1 is that, and m2 is just m. So force, when their distance r, this thing, force is just equal to k m1 m2 r to the power 4. So this actually many dipoles, the force really drops pretty fast. So using k, and you have a cube 1 over r cube and times m, and then you have another m and r to the power 4. So this whole thing is k a cube m square 1 over r to the power 7. And this is important. So when I do this integral, so when I do f dr, this is going to be minus f dr infinity to r. This is going to be k a cube over 6 m square over r to the power 6. So looking over here, looking over here, I see this as the answer. So the answer is C. Now there are lots of little details that you have to be kind of making choices, and one can get confused. So what is this problem trying to actually test? You know, I was trying to ask that question myself. So as far as I can see, this problem is trying to see that if you can think in terms of magnetic flux, okay, and whether you can think like this to this transition. That's how current in a loop to corresponding magnetic moment. That one thing that you if you think like that, then it's really not that difficult. And then that energy is related like this. That's the third thing that this is trying to test. I suppose I see part one is just balancing, and you I suppose as long as you know Biot-Savart law, how to use it, you don't have to memorize it, just use it on the spot. You'll be okay. All right, I think that's it. If you haven't subscribed, I will really appreciate if you can subscribe. It helps the channel grow. If you like this kind of explanation, a detail, alternative ways, different paths to the same problem, I would appreciate you hitting the like button. There is much more at my website at physicsbootcamp.org. You can check that out. Its entire textbook is freely available. I'll see you in the next video. Bye.